So in continuation with our previous topic on the magnetism, here are some essential things that I'm describing. So if you take a look at the periodic table, there are a lot of elements belonging to this. And here you can see then that you are having the ferromagnetic materials only in the three atoms, that is the ferrous, cobalt and nickel. So these three elements constitute most of the Earth's crust and permanent magnetic field also. This one is antiferromagnetic. That is why, remember where it was used. This is used in lasers. So they have got different property, and you can see a lot of diamagnetic materials. Diamagnetic material, in fact, they are not purely magnetic in nature, but they have got the magnetic property, which is not very strong. And I think I just told you how the paramagnetic and diamagnetic substances simply pass through. If you have a north pole and south pole like this, and you place, let us see what this diamagnetic is in, right? It was green in nature. So if you place a diamagnetic substance here, the magnetic lines of force will pass above this. It was going into this because it doesn't have any magnetism. They just go like this. They don't pass like this. But if you have something like paramagnetic material, with paramagnetic material, the lines of force will tend to pass through this like this. Okay. So where are those materials? The paramagnetic materials. Oxygen is paramagnetic in nature. Aluminum and stand out in large manner. And this apart, you've got a few elements like sodium, magnesium. They show the paramagnetic behavior. So the periodic table is classified into that. And before going into this beautiful diagram explanation, let me take up a few things like, for example, the magnetic permeability. So if you need magnetic permeability, so you have this light. It is calculated as F, the force of attraction between two poles, as equal to P1 into P2 by Q r square. Okay, Q is known as the magnetic permeability. Q is known as the magnetic permeability. R is the distance between two poles. Distance between two poles, and P1 and P2 are these two, the two poles of the magnet. You can consider it as a bar or something. And the constant that you have here is Q, can be taken up as some constant, which is which comes into the force when you equate force with the two poles. That is the strength of the two poles. Okay. For vacuum, you have, for vacuum, Q is equal to 1. For other media, it may be greater than or less than 1. Okay. And the important thing is, for air, Q is equal to 0. For vacuum, Q equal to 1. For other media, it will be greater than 1. For air, it is approximately equal to 1. It is a measure of tendency of maybe less than or equal to 1, and it measures tendency of magnetic lines to pass through. Okay, so here is this one, that is, they are passing through this, right? They are passing through. You have North Pole and you have the south pole, which is magnetic field. How much magnetic lines of force pass through, and how are just so many are repelled. If they are repelled, they will be in the upward direction like this one. If they pass through, they will pass through this medium and like this. Okay, the next important factor that I'm going to discuss is the magnetic flux, which you have seen. Suppose if a substance is placed in a magnetic field, the substance is said to possess a magnetic field which is given by the strength of the field, strength of the magnetic field, which is equal to H. Okay. Now magnetic permeability is equal to Q, and magnetic induction as a result of this magnetic induction, because you have placed the material inside the magnetic field, uh, that we call it as a flux. This is field is called as a flux. Now is equal to B equal to HQ. This is the equation that okay. Now close on these lines, you have to calculate the intensity of the magnetic moment. The total magnetic moment per unit volume, magnetic moment per unit volume, that is induced. Induced means you have to undagirdu the medium in the substance field by strength of H gas is known as induced of by, that is by H gas. Gas is the unit. By H gas is represented by the symbol I is equal to I. Okay. Now because I have told about this volume susceptibility. Susceptibility na எவ்வளோ மேக்னட்டிசம் அதுக்குள்ளே உண்டாகும்னு சொல்கிறாங்க. இப்போ ஆக்சிஜன் கொடுத்துருக்கோம், நைட்ரஜன் கொடுத்துருக்கோம். இதில் உடனே மேக்னெட்டிக் ஃபீல்டு வச்சாக்க மேக்னட்டிசம் வரும் அப்படின்னா ஹை சசெப்டிபிலிட்டி அப்படி சொல்லுவாங்க. Now consider a substance placed in a magnetic field. Substance placed in a magnetic field. Substance placed in a magnetic field of a strength H. Okay. And the flux is B. The flux is B. Then the intensity is given by B is equal to H plus 4 pi I. Here is the intensity I. B equal to H plus 4 pi I. And this ratio B by H, when you just bring the H towards this size, is equal to magnetic permeability. So it goes, you have to just bring this quantity H downwards, and likewise if you divide this B by H, you have to divide every factor by the same thing. Here it is. So grid put by B by H equal to H by H plus 4 pi I by H. Okay. Now this H by H is actually, it's going to be 1, right? Therefore B by H is equal to 1 plus 4 pi I by H. Okay. Now it turns out that you have a separate quantity as B is considered to be Q. B is considered to be Q. You have a separate quantity for I by H also. V by H is equal to Q. I'm sorry, this is I by H. It should be I by H. And this turns out to be a new quantity called as the K. Therefore, intensity of magnetism. Intensity of magnetism, that is what we have given, is proportional to H, or I is equal to KH. This K is what you bring here. Okay, and K is called as a proportionality constant. K is called as the proportionality constant. So finally it turns that B by H is equal to Q is equal to 1 plus 4 pi K plus 4 pi K. Okay. Now this thing will, the diagram which we have seen is will be going to be very much clear. But before that, let me just tell you that we started this as the volume susceptibility, magnetic susceptibility per unit value, magnetic susceptibility per unit value is called as the volume susceptibility. Volume susceptibility. Now there is this is about the volume. Then we are going to see something called as the mass susceptibility also. Once you have calculated mass, this volume, there will be the option of calculating the mass susceptibility also, because you will have density also. Mass susceptibility is given by this word chi. So this is pronounced as chi. Chi g is equal to K by rho. So K we have already seen, volume susceptibility. Where is it? Okay, so it goes to this volume susceptibility, right? K by rho is this. So now this is the density of the substance. Density of the substance. So the mass susceptibility also represents the induced moment per unit volume. Induced moment per unit weight per unit field. So these are all some of the constants that there is there. Okay, therefore B by H is equal to Q is equal to 1 plus 4 pi kg into rho. I think how you got this rho. Right, this rho. We have just substituted K. Okay, K is equal to chi g into rho. That is what we are bringing it this particular place there. Okay, since Q is the less than 1, since Q is I think it less than means it is greater than 1, for the magnetic materials, magnetic materials. Mind this, these are the important things. Para and ferro, not there, doesn't come there. para and ferromagnetic materials, chi G will be equal to positive. This is what we are going to see in the above diagram. Just have to keep it in mind. And for diamagnetic materials, chi G is equal to negative. Chi G is equal to negative. And then followed by this is another quantity we have got called as the molar magnetic susceptibility. Molar by molar means, what is molar? 1 mole of the substance particular that substance is called as the molar. So you have to take that mole quantity there. And because we are taking chi molar is equal to chi G. Chi G is here. Okay, just magnetic moment. That is due to mass. This is due to mass or weight, whatever it is. Chi G into yam. So this stands for the molecular weight of the substance, therefore. So it is expressed in units of cc per mole. It is expressed in units of cc per mole. Therefore, atomic close on this, if you have got atomic, this chi A will be equal to chi G into A. So A will be equal to atomic weight. When you want to subsidize the magnetic susceptibility of an atom, then you have to just multiply this. Now, atomic mass we have defined as a magnetic susceptibility of 1 gram atom of the substance. Similarly, molar magnetic susceptibility will be defined as 1 mole of the substance. So this is 1 gram and this will be 1 mole of the magnetic substance. What are those substances? We are going to just see, go back to the diagram there. Those substances are diamagnetic, ferromagnetic, paramagnetic, antiferromagnetic, etc. Okay. So I'll give the description of these into the in the video section of that, so you can have a look at this. But before that, let me just tell you what we have to do with this diagram. So here you see, I'll just go back to the diagram part there. Oh, here it is. Okay. So you have seen the magnetic field. So just starts with the diamagnetism. How much it is susceptible? I think I told you with the susceptibility chi m is negative there, right? You just saw this chi m. If it is mass and chi a, if it has atomic sign, then it is small and negative. Susceptibility will be equal to small and negative. This you have to remember. Their atoms have no magnetic moment, and that is not represented by any domain there. So these things are called as the domain. Okay. Then this is the magnetic behavior. So the behavior increases. This is the H. I think we know it as the field strength there. Field strength TH. Field strength there. So it increases, and magnetism also. If you increase the field strength, the magnetic susceptibility and the final magnetic behavior of the substance increases. So that means if you have a diamagnetic substance, whatever amount of magnetic strength you increase, there is no increase in the magnetic field there. Rather, there is a small line that goes below that. You see this line there, right? This line there. So it's going negative in the negative direction. So this is the property of the diamagnetic substance there. Okay, compare this immediately with the paramagnetic substance there. Here in the paramagnetic substance, you have chi m is positive there. So it is positive there. So atoms have randomly oriented magnetic moments. These magnetic moments, when they come across, they can cancel. They can cancel. But because their magnitude and direction are different, note this particular point, they can cancel, but the and magnitude and direction vary, therefore they do not cancel. So you can see, as you increase the magnetic field strength in this x-axis, H magnetic field strength is increased, the magnetism is slowly being induced into this, so it slowly increases there. So some examples are the stainless, platinum and manganese. The values are given. This is the chi values that are there, and you can just see that it is about 0.19 into 10 power minus 6. So it is either it can be moles or the grams depending on how much these things you take. So therefore this paramagnetism is defined by this positive value there. Okay. So then you have got this ferromagnetism. So this is we call this as the naturally occurring there. Naturally occurring there. Ferromagnetism, large and positive function of the applied field, microstructure dependent, and that is the atoms have parallel aligned magnetic moment. So this is an important point there. So you can see these round things are all we are called as the domains there. Okay, these domains, all are getting arranged there. So the arrangement is very strong there. So they contribute to the magnetic field. One of the best example is ferrous, and cobalt also goes into that. A lot of cobalt isotopes in the earth cobalt 56 that also constitutes the magnetic moment, but nothing like iron. And look at this value is about 1 lakh. The susceptibility value is 1 lakh. So that means the ferromagnetic substance is the most strongest compared to the paramagnetism. But paramagnetism has got its own functionality. So if you have an arrow like this, if you put an exact arrow opposite of this, like this one, okay, like this one, these two can get paired and get cancelled. Well, that is what we do see here. You can see that this is getting cancelled there. Magnitude and direction both are same. These are the things are getting cancelled here, and this are getting cancelled here. So everything is getting cancelled, and that is what you get in the antiferromagneticism. This also I got a small positive value, but still because of some uh, discrepancies in the domains, these are all the domains which I am telling you. Here you can see that if they are adjacent, they can cancel very well. If they are not adjacent, they do not cancel very well, and they result in some small positive value towards the magnetic field. As you apply the strength, magnetic field strength, the magnetism increases. But in this case, where ferromagnetism, it abruptly increases. So it's a very sharp increase, and then it remains the same. So this is a saturation level we have already seen. Okay, in the last part of the ferrimagnetism is due to some atoms such as ferrite there, barium ferrite there. It has a value of about 3. Here it has got a value of 3.6, 10 power minus 6, so approximately 3. Atoms have antiparallel aligned magnetic moments, and as a result, they get cancelled here. So I can put this ferrimagnetism as huge values there. Okay, huge value. Okay, it runs in thousands, and therefore, the whatever amount of cancellation is there, it doesn't affect that. Okay, I'll just put it in a different way also. Suppose if you have something, want to define it like this. Okay, this one plus this one, they get cancelled. Okay, they get cancelled. And suppose if I have something like this one, something huge, and then a small, the resultant of this is this plus this will be equal to something like this. The result of this will be something like this. So ferrimagnetism, uh, this one, ferrimagnetism depends on the change in the magnitude plus numbers. How much is the number? Suppose if I have something like this, okay, I'm just going to put some 2 or 3 upwards, and then 1 downward and 2 downward. The resultant is only 1 upward, and this is also contributing to the ferrimagnetism. This is also contributing to the ferri, and this one is also ferri. This one is the diamagnetism. There is also one more aspect added to this. Okay, if you change the magnetic say for example, if I have some electron like this, and then another electron just going this direction, another electron going just in this direction, the resultant will be, because in magnitude these two will not be equal, there will be some magnetism. Resultant magnetism. Okay, so this is so much about the magnetic field strength, and you can go through again, find your notes somewhere there. In the next part, we are going to see the effect of temperature and to the magnetic property. Okay, so I think it is clear. If you have any doubts, you can get back to me. Thank you for joining me. See you soon.